Right. Hi, everyone. My name is Abhishek Gupta, and I'm here to talk to you guys today about meta-reinforcement learning for structured exploration strategies. So exploration, as we all know, is an extremely important problem in deep RL. It's important in order to experience and optimize the sparse reward functions to learn quickly and effectively, but it's still done in a kind of naive way in many cases. So if you see here, we have TRPO trying to have the humanoid run around and guided policy search exploring some object manipulation. It still seems kind of naive. It's doing a lot of things which are not directed at all. On the other hand, if you look at a baby exploring, they're doing things which are much more directed. So they're actually picking up objects and doing things which are not just random movements of their arm in space, right? And one hypothesis why this happens is perhaps they're able to integrate their prior experience in order to synthesize better exploration strategies. So the question we ask in this work is, can we use our prior experience in order to learn better exploration strategies? So to make this a little more concrete, let's consider an example. So let's say you have a robot. It's learned to pick up these different blocks as shown on the left, right? And we have a new scenario with a lot of different objects. And the goal is to pick up one of the objects, but it's unknown which one it is. So a reasonable thing to do is to try and pick up different objects rather than wave your arm around randomly in free space, right? And so keeping this intuition in mind, let's formulate a problem. Let's say you have prior experience on some tasks, T0 to Tn, which are drawn from a distribution of tasks P of T. And each of these tasks is an MDP with some reward function, let's say Ri. Right? They're all in the same environment. Now that you get a new objective, where you have a new task T test, where the reward function is R test, and it's drawn from the same distribution. Now, the point is that you want to learn as quickly as possible on this new task, but the reward function could be extremely sparse. And the sparsity introduces some challenges. Firstly, you need to have an extremely effective and directed exploration strategy. So you need to do things that are likely to get you reward. When you do get reward, you want to be able to use this reward and adapt quickly for your new task. All right, so in this work, we offer two key insights. The first one is that we're changing our source of exploration. So instead of exploring the space of random actions, we're exploring the space of random but structured behaviors. Right? So we want to go and pick up different objects, but we don't want to wave our arm around randomly in free space. The other thing we want to do is we want to quickly adapt our behavior to new scenarios once we get the actual task rewards. Right? So the first one we'll refer to as exploration, and the second will be adaptation. So the first question becomes, how do we actually generate coherent exploration behavior? So the first thing we notice is that burst time sub stochasticity, like most deep RL methods used right now, is unlikely to yield meaningful behaviors. And this is probably because a policy is changing its mind at every single time step on what it wants to do. And this is unlikely to go and pick up an object all on its own. Instead, if what we do is introduce time-correlated stochastic noise through a latent space, this allows us to do more meaningful things. So the things that we want from the latent space are that firstly, we wanted to capture the distribution of prior tasks and generate these temporally coherent directed behaviors. So we might imagine that sampling from the latent space might generate behaviors like, let's go and pick up these different blocks, right? And the second thing is that we want the latent space to be such that adaptation is extremely quick. So once we get rewards, we want to adapt extremely quickly. And this is something we'll cover in the next section. But first, in order to introduce this latent space, we introduce this notion of latent condition policies. So latent condition policy is the same as a regular policy, but which is taking in a state, it's generating an action, but it's also conditioned on this latent variable z, which is sampled from some latent distribution, right? And so this introduces this notion of temporally correlated noise because it's only sampled once per episode while the action is sampled at every single time step. So what we'd like from this latent space is that stochasticity in the latent space generates behaviors which captures the distribution of prior tasks. So it's temporally coherent directed behaviors. So what we'd expect is that one sample goes and picks up the red object, one picks up the blue object, one picks up the square, and so on, right? And this allows us to then explore in the latent space rather than exploring in the action space. So how do we train something like this? Well, we might imagine, we can think of this as a generative model. So you have a latent variable z. The policy can be thought of as a non-differentiable decoder, and you want to decode into a set of different behaviors. So over a number of prior tasks that you have, you can train this as a generative model using things like variational inference. But this doesn't answer the question of how we actually adapt quickly to new tasks. So what we're going to do is we're going to borrow some tools from meta learning in order to train our latent space. The point here is that we want to explicitly train our latent space for quick adaptation. So if you get a new task, you want to be able to quickly adapt to that new task using one or a few steps of gradient descent. So let's say we have a latent space where we have different samples giving us these different behaviors, and we get some reward for reaching the red ball, right? So now with one step of reinforcement learning, we want to change our latent distribution significantly so that all of our samples are now sampling around the red ball. And given this, we can then backpropagate through the reinforcement learning process to get a better latent condition policy, which is going to enable this, right? So to make this a little more concrete, what we want to do is train a latent policy pi theta across multiple tasks and have a latent distribution parameterized by omega I for each of the tasks. And what you want is that after one step of gradient descent, you're optimal on each of the different tasks while constraining your latent distribution against a prior. You want to constrain against a prior because on a new task, you just want to sample from the prior for exploration. And so a method like this allows us to combine the benefits of fast adaptation that come from this meta-learning procedure with structured exploration from the latent variable model. So when you get a brand new task, all we need to do is just do reinforcement learning via policy gradient. So we initialize our latent distribution back to the prior, and then we just do policy gradient to do adaptation. Right. So in order to empirically evaluate this, we looked at 3 different environments in simulation. So we have a robotic manipulation environment where you have to push blocks to some goal. You have a wheel locomotion environment where you have this differential drive robot which has to drive to different points. And we have an ant robot which is trying to walk around to different points. And the distribution of tasks that we trained on are shown at the bottom. We have blocks shown in the orange region and goals shown in the blue region, and each task is pushing a different block to a goal. And for the locomotion tasks, you're trying to go to these different points along a semicircle. And the point is that the reward functions are quite sparse in all of them, and in order to even experience the reward functions, you need to do directed exploration. So the first question becomes, are we actually able to learn quickly on these tasks which have sparse reward functions? Right, so over here we plot the performance at meta testing time, so we're learning new tasks. And we plot on the x-axis the meta testing iterations, on the y-axis the accumulated returns. And we see that our method, which is shown in blue, is able to learn extremely quickly and learn better than all the other methods. So we compare against learning from scratch, using exploration methods like VIME, using meta-learning methods without this structured stochasticity, and using latent space policies without meta-learning. And we find that we're able to do better than all of these methods because we combine fast adaptation along with the structured noise. So we get the benefits of quickly adapting and exploring in a more directed way. What's more illuminating, perhaps, is the actual exploration behavior we observe. So we see that we can plot the behavior by plotting the position of the pusher and the position of the center of mass of the ant. And our method is generating these directed behaviors. So we see that we're actually pushing blocks from the orange region to the blue region rather than just randomly moving around. And the ant is actually able to walk around to different points along the semicircle, which makes it much more likely to experience rewards. A third piece of analysis that we have is how does the policy behave when you have noise versus when you don't have noise. So if you take the latent space and you don't inject noise into it, you get exploration like on the left. But when you do inject noise into it, you get a much wider distribution of trajectories, which is much more likely to experience reward and adapt quickly. Right, so given that we've covered all these things, what are some takeaways? Well, firstly, you want to inform your exploration with prior experience when it's available. And meta-trained latent variable models might provide us an efficient way to do this, which combine good exploration with fast adaptation. With that, I'd like to thank my collaborators, and I'm happy to take questions.
We have time for one question.
Thank you for the talk, and your method seems to be far better than other methods.
Yeah.
What's the catch?
Well, the catch is that none of the other methods even experience any reward. And so they're not really exploring effectively enough to experience reward when it's that sparse. And so if you see learning from scratch and you give it enough time, it does eventually go up. But our method is using all of its prior experience and is actually exploring a lot more effectively, whereas the other methods are not able to capture that. Thanks.
Next, Marlos is going to talk about count-based exploration with a successor representation.
I'm Marlos. I'm going to talk about how we can use the successor representation to do exploration in reinforcement learning. This work is in collaboration with Marc, Bellemare, and Michael Bowling, my supervisors. So let me first start with some background on the successor representation. So it was proposed in 1993 as a representation learning algorithm. So we're trying to get basis functions to estimate value functions in reinforcement learning. And the idea is that when you look at most of the representation learning methods, when we are doing regular supervised learning, for example, what we are actually trying to do is to assign similar values to states that are closed in space. So in this case, for example, let's ignore the color of these tiles. You would say that A and C because of generalization, they tend to have a similar value than A and B, for example. But then, of course, if we think about reinforcement learning, getting to B, it's way easier than getting to C from A. And what the success representation actually encodes is this proximity in time instead of the proximity in the Euclidean distance, let's put it this way. And then if you plot it and you compute the success representation, that is what it looks like with respect to A and the random policy. And basically what you have is that you have the states being assigned a similar value to those that are close to A. And formally speaking, you can define the success representation as a sum of the discounted number of times you visit a state, a given state. It's always defined with respect to a policy pi and to a transition dynamics p. And what is cool about the success representation is that it also has a closed form solution. And in reinforcement learning, we see this equation all the time. It's the LSTD matrix and all sorts of other places that we actually, because we can basically just compute the value function when we have this. And also, we can efficiently estimate the success representation when we're using TD, to compute the success representation with respect to a state. And basically, if you want something to fit in a box, it's like the success representation is as if you're seeing a reward of 1 every time you visit a specific state on the environment. So what we did in this paper, and the main idea of this talk is that we introduced this concept of the substochastic success representation. And all we are doing is that imagine that you have this MDP with 3 states, very simple, and we are going to imagine that there is another phantom state and this phantom transition is going to these MDPs. In a very similar flavor to what RMax does, for example. And then what we are going to do is that we're going to compute, we can compute the empirical model of this matrix P, adding a +1, which is like as if you had observed this transition going to this phantom state once. And the idea is that, and the reason it's called substochastic is because obviously these rows don't add up to 1 anymore. But the intuition here is that, well, if I do this, I can actually start to count state visitation. And this is what we show in the paper, and the intuition is that imagine that you're in state A, and you can actually go from, and you're going to start initializing things with a uniform prior, so there is a 1/3 chance that I go to B, and a 1/3 chance that I go to C, and there's a 1/3 chance that I go to this phantom state. As I keep visiting A, I always observe transitions from B to C, from A to B, or from A to C. So it keeps getting thinner, this transition, and how thin this probability is how many times I've been to this state. So it's a proxy for that. And then I had just defined the substochastic matrix, but then of course we can define the substochastic success representation in a similar way. So doing this, we basically had this theorem in the paper that is showing that imagine that you have this MDP or an MDP for what it's worth, and then you have visited a state S2, S3, S3, N of S2, and S of 3, and S4. And now what we can actually show in the paper is that if you can actually compute the substochastic representation, what it's actually doing with respect to state S1 is a sum, is a discounted sum. It's just like a return where you are going to observe a reward of 1 over the number of time steps you've been to that state as a reward. And then now it helps us to do exploration, right? Because now if we want to visit states that we have visited the least often, we can do that with the success representation. So there is a theorem here. I'm using quotation marks because I'm just simplifying what the real theorem is. But basically what we're saying is that, hey, the substochastic success representation, what it's actually doing is computing a return over the number of time steps I've been to each state. And then the reason that matters is that, okay, so now let's do some sanity check following Ian's recommendation early this morning. And it's like, okay, so the sign here, it's related to how things go in the theorem, but the point is that let's give an exploration bonus that is proportional to how many times I visited this state. And we are going to do this in RiverSwim. Well, I mean, in the paper, there are more examples in the tabular case, but it's very well-known and challenging domain that basically, if you go all the way to the right, you get a large reward of 10,000, but then you're trying to swim upstream, so it's very likely that you're going to end up on the left side anyway. And if you try to go left, you actually end up on left because you're swimming downstream, and then you see a small reward. So Q-learning is completely hopeless in this type of setting. And what we actually do is that when we compare our algorithm to traditional algorithms in the field that have PEC, MDP guarantees and stuff like that, we perform as well as they do. But the reason this matters is that, well, of course, if you want to count state visitation, why don't you just count them? Why do you actually have to go through all this great length of defining the substochastic success representation and stuff like that? And the reason is because we know how to compute the success representation also using neural networks. I have papers in the past, and other people have papers in the past on how we can actually compute the success representation. And this gets to the flavor of generalization, right? I mean, we can't just expect to visit every state, so how do we generalize? So there's a fancy neural network architecture. If you actually want to understand the reasoning behind the architecture, go to my poster, it's close to the exit door, and then I can actually explain why we have all these heads. But the intuition is that we basically have DQN is one of the heads. The other head is estimating the successor features. And then we are adding an auxiliary task to drive the representation learning process, because otherwise, since the representation is the one driving the exploratory behavior, we can't just be without it. And then we just use an exploration bonus that is 1 over the L2 norm of the successor features. That's a fairly simple addition. Then you can simply do DQN. If you look at results, I don't like to give bold numbers because these are very few seeds. We ran it 10 times, and I was super proud that I was able to run 10 times. But the message is, we are competitive to, as far as I know, the best results that we have on exploration and Atari that are using these pseudo-count-based methods from Marc, Bellemare, and DeepMind in general, like Jorg Ostrovsky as well. But they do require a density model, which is a very complicated thing for you to do, and then it's domain dependent. And this approach seems to be fairly general, and actually if you want to hear about how I train these things, because it also seems to be relatively robust. So just to I asked Ian the wish list, and I lightened the check marks because I don't want to say that we're doing all this. But basically, it's like I'm really excited about this direction, and I think that there is I think it's a very different direction from what other people have done exploration. But it seems to pass the simple sanity checks. We are being able to do some generalization with these neural networks, and it is computationally efficient. We are just doing DQN and sample one-step methods like TD. So I'm excited about this, and I think that there is a lot of work to make this better, but I think it's a promising research direction. So with that, I want to thank everyone, and I have questions. I take questions, but the video is, I can't request access to myself if I'm not in the laptop, so just failed. Okay, I'm sorry. Questions?
We have time for 2 questions.
Emma, over there.
This is really nice work. It seems like the performance still isn't what we want the level to be at really hard exploration problems like Montezuma's Revenge. What are your ideas about how we need to scale up further exploration in order to tackle those problems efficiently?
I think that the problem of generalization is essential on how we tackle these exploration strategies. And even in Montezuma's Revenge, we kind of gloss over how important generalization is, and we keep hoping that we're going to visit all states or visit enough states to get there. I think that if I wanted, I could get much better results with those things, because I didn't try very hard to optimize any of those parameters, and it was just like, okay, it seems to be working, and I'm happy with that, because I just want to get the results that are comparable. But yeah, honestly, I think that we almost need a paradigm shift, because I think, and the reason I'm excited about this work is because I see it as the exploration drives the representation learning process, and that the representation drives the exploration. So you have this intertwined process. And I think that we need something related to that, because eventually we would get to something like objects, and then something like, for example, what you were able to show in the pitfall recently, that it's like, okay, we have this, and now we can do much better because we actually have a good representation of these objects.
Let's take time.
Is there a USB? Do you have USB? Hello, everyone. My name is Qijing. And today I'm going to talk about our recent results in answering a very basic question. Is Q-learning provably efficient? And this is a joint work with Zeyuan, Sebastian, and Marc. Okay? First, there has been a very long debate between model-based and model-free reinforcement learning. As we know, for model-based reinforcement learning, you're first learning a model of transition model, which is a model of environment from the experience, and then it updates policy and value based on the model you learn. And for the model-free reinforcement learning, it just directly skip these steps and directly update the policy and value. Definitely, there are a lot of benefit for model-free reinforcement learning, which definitely is simpler because you don't need to build the model of the environment. It's also more flexible because you can directly parameterize the policy and value, and you no longer care about the environment. And so based on this reason, that's why it's more prevalent in the modern reinforcement learning, deep reinforcement learning. But also, on the other hand, a lot of people believe there should be no free lunch in this scenario. So people think because model-free algorithm, they don't really build a model environment, so it should be less sample efficient. That means in order to learn some reasonable policy, you actually need to allot more samples. So this point is actually supported by some recent like empirical work. They also say the same. So the first thing we would like to ponder is this less sample efficient real? So the real question we're going to ask is, can model-free algorithm be made sample efficiently? In particularly, we want it as sample efficient as model-based algorithm. And we're interested in a very classical model-free algorithm, which is called Q-learning. And we're wondering, is Q-learning provably efficient? Okay? And surprisingly, this question seems very basic and fundamental, but yet it remains unknown even for a very basic scenario where you only have finite state and finite actions. So a lot of people, when hearing this, some reaction of my friends is always like, what? Is this real? Then isn't like tabular MDP already completely solved? Unfortunately, the answer is no. So the first, I would like to tell what we did know about tabular MDP. So for a lot of past 10 years and 20 years, there has been complete study of some model where like either infinite horizon or finite horizon MDP, where you actually need to know all the possible states and you are given a simulator or a sampler, where you can basically feed any states you want and feed any action, and what you get is the next states and the rewards. And definitely, given all the possible states and simulator, this problem it should be much easier than standard reinforcement learning, because just imagine a scenario if you're playing some entirely, completely new game, and you have no idea what is the next chapter gonna be, so how could you know all the possible states and not mention like you don't have any simulator? So this problem is more or less in the community believed as a planning task which does not require exploration. So what is a more challenging problem that kind of like have all the essence of reinforcement learning is this one, episodic MDP. So it's just basically MDP where you also have the states and action, but basically you play each game as an episode. And the only difference is you have finite horizon, so each episode only have H steps, okay? And you still have a transition matrix, you still have a rewards function. And in our setting, we're very flexible. So basically you can have different transition probability and also different rewards in different time steps. And for the simplicity of this talk, I'm gonna fix the first states. In our paper, we definitely allow some adversarial chosen. So the difference between this model and the simulators, now you're only allowed to pick action, which is what you actually do in the real world, and you not have the freedom to pick states. okay? So the target in this model is we want to minimize the regret, where regret is defined as a summation of the difference in terms of value function between the optimal policy, where it's a V star, and the policy you're gonna play at episode K, okay? Some of you may wonder, we always talk about sample complexity till now, but why now suddenly change about the regret? It turns out regret is actually a stronger version of sample complexity because there's some theorem basically saying for any algorithm you can prove some regret and you can translate it into some algorithm which directly gives some sample complexity, okay? Basically how many samples you need to learn a good policy. The fact you need to know is whenever you get a square root of t regret, that means you get 1 over epsilon square sample complexity to find epsilon optimal policy. And the worse regret you get, the higher sample complexity means you need more samples to learn. The bad is worse, okay? And what is known about episodic reinforcement learning? They actually have a lot of recent good results, but most of them focus on the model-based algorithm, which you need to build a model of environment, transition matrix. And most of them already getting the regret, which is square root of t, which is good. And on the other hand, for model-free algorithm, it's actually far less understood. For example, a lot of people always criticize Q-learning with epsilon greedy. And they're saying if 0 initialized, you actually need epsilon, the regret is actually terrible, which means you need exponential in steps, which is exponential in age, which is basically you cannot tolerate. And the only result that's polynomial we're gonna find is an algorithm called delayed Q-learning, which gets suboptimal regret, which is less sample efficient as model-based algorithm. So what we did in this work is we still studied Q-learning, but instead of epsilon greedy, we proposed another exploration strategy, which is use UCB, and which is upper confidence bounds. And this one, we're the first time in the model-free algorithm class, we're getting square root of t regret, which is more or less almost as sample efficient as model-based algorithm. We have 2 versions. One is Hoeffding version, one is Bernstein version. Hoeffding version is much simpler in terms of algorithm, and Bernstein version is sharper in terms of regret. Okay? And we're not only matching the square root of t, if you look at the state action dependence, we're also matching the best model-based regret. And the only thing we're gonna lose is 1 square root of h factors. And I also want to note our algorithm is much better in terms of time and space complexity compared to all the model-based algorithm. Okay. So finally, I'm gonna talk about what is secure learning with UCB, what's the difference between epsilon greedy. Okay, so it's still very similar to epsilon greedy. We still keep track of the Q value for each state action and each step of the game. Okay. And in addition to that, we also need to keep track of a counter, which kind of like count how many times you already visited the state action at that step h. And the key step here is basically this update equation, which is similar to the Q-learning, where you're still doing incremental update. You have a large portion of previous Q value, and also small proportion of like recent updates. And the only difference we're gonna get is we also adding some exploration bonus to the current update, where BT is our exploration bonus. BT is 1 over square root of t, where t is basically our counter, how many times you already visited this state action. So what this kind of thing is saying is kind of like saying if you haven't visited this state action very often, you only visit it once or twice, then you're adding a very large bonus, which means like saying, oh, I'm not sure about what I estimate about this Q value, but I'm optimistic. I think it might be very high. But if you visit a lot of times, then you think, oh, my estimate is very accurate, so I should be fairly certain about it, so I'm only adding a very small bonus. And because we're already adding bonus here, when we take action, we no longer do any epsilon greedy. We always take greedy action with respect to the Q value I maintain. And the other thing I want to mention is our learning rate is h over t instead of 1 over t. T is also how many times you visit that state action. So finally, I'm gonna talk about the theorem. Theorem is more or less saying the algorithm I just presented have a very good regret, where regret is square root of t, okay? And this iota is a log factor. So I want to mention 2 key points around this theorem. The first one is definitely we should use better exploration strategy, which is UCB instead of epsilon greedy. This UCB allows you to try less terrible actions, and so based on the previous rewards. And the other thing is we found actually in order to prove this efficiency results, the learning rate can be very delicate. And the reason is because if you look at these updates, the alpha t is more or less like the balance of the recent updates and all the previous updates together in the previous queue. So if you pick alpha learning rate to be too large, it emphasizes too much recent update, and it has a lot of variance because the reward is stochastic. And if it's emphasized too much of previous one, then you introduce a lot of bias because previous one is inaccurate, okay? So basically, other thing doesn't work. Only H over T give you the right balance between bias and variance. Okay, so the takeaway of this work is definitely model-free algorithm now can be as sample efficient as model-based algorithm, at least in the tabular setting. I think this concludes my talk. Thanks.